This is 40 Days of Chemistry, Part 6. This one's not even going to be anywhere near close to 5 minutes. Let's just see how we go. This one is looking at 9.4.2 again, the Haber process focus area, but this time we're just going to focus on the chemistry of rates and yields of reactions. And the first thing is rate of reaction. You need to know the rate of reaction is the number of reactions occurring per unit time, e.g. the number of reactions occurring per second. And rate of reaction is very closely linked to something called activation energy. If you recall our enthalpy diagrams, we have here the enthalpy of the reactants, enthalpy of products. This is an exothermic diagram because delta H is negative. The activation energy is that initial energy you need in order for the reactants to turn into products. So that's the activation energy, that little EA there. Now, at any given temperature, there's a distribution of particle energy. So all particles of a gas, for example, in a container, don't all have the same energy. They've got a range of energy. So you'll have some particles, only a small number of particles with very small energy, only a very small number of particles with very high energy, but most of the particles here have some sort of average energy. Now, at any temperature, only a fraction of particles have energy greater than the A, represented by this little purple section here. And particles can only react if their energy is greater than or equal to the activation energy. And therefore, the rate of reaction is controlled by the proportion of particles with energy bigger than EA. And that's the critical concept for understanding things that affect rates of reaction. The rate of reaction is controlled by the proportion of particles with energy greater than the activation energy. Just a little aside here, this is just a reminder of what rate of reaction looks like. In any reaction, you've got reactants and products. At the start, you've got lots of reactants and no products, and over time the amount of reactants drops away and the amount of products increases till, in the case of equilibrium reactions, it reaches some sort of equilibrium at a certain time. Now, in these sort of graphs, rate of reaction is the gradient, because rate is the change in concentration over time, or the reactions per second, and therefore the gradient is the rate of reaction. As you can see here, in early times or very short times, the rate of reaction or the slope is quite high when there's lots of reactants and the product is still being made, but over time the rate of reaction or the slope decreases over time until eventually, when you reach equilibrium, the rate of a reaction is effectively zero because there's no net change in products or reactants in their concentration. So let's look at the factors that can affect rate or affect the number of particles with E bigger than EA. And the first thing is temperature. This is just a recap from the previous page, but the key thing about temperature is as you increase the temperature, you increase particle energy. That means all the particles get more energy. So that whole curve shifts to the right, or shifts to the higher particle energy end of that diagram. Now what that does, as you can see here, here's T1. The initial temperature was this temperature here, so the particles had this initial energy profile. As we raise the temperature, all the particles gain more energy. So still the same number of particles, just they all get more energy. And what that means is, if this is the activation energy here, because the curve has shifted towards the right, that means now we've got more particles with energy greater than the activation energy. So at T2 here, which is the greater temperature, there are more particles with energy greater than the activation energy at T2 compared to T1. Therefore, the rate is higher at T2, i.e. the rate is higher at higher temperatures. Next thing is concentration and pressure and surface area versus rate. Now, if you increase the concentration of a solution, or you increase the pressure of a gas, or increase the surface area, but not the amount of a solid, what you're doing is you're increasing the number of particles per unit volume. And if the temperature is constant, and that means the particle energy distribution remains the same, but because you've increased the concentration, or you've increased the pressure and you've increased the surface area, that means there's more particles at each energy. So what you're doing is not shifting the curve left or right anywhere, but because you've got more particles in a certain volume, you're increasing the concentration or number of particles at each particular energy. So the higher concentration means more particles at each energy. Now, because of that, because we've got more particles at each energy, that means we've actually got more particles full stop with energy greater than the activation energy. And therefore, as we increase the concentration of a solution, the pressure of a gas, or the surface area of a solid, we have more particles with energy greater than the activation energy, and therefore the rate of reaction increases. And lastly, looking here, this is catalyst and rate. Now, a catalyst, as we know, participates in the reaction, creating a reaction pathway with lower activation energy, and the catalyst is reformed at the end of the reaction. It's not consumed. And this little enthalpy diagram here shows you that little blue pathway. It's another pathway of the reaction with a lower activation energy. Now, how that affects the actual reaction itself? Well, because the catalyst increases the rate of reaction, it just means these gradients are going to be steeper. So the gradient actually starts off much steeper, and it reaches equilibrium here in a shorter time than normal. So catalysts increase the rate of reaction. They don't actually change the position of equilibrium, though. We're going to talk about that a bit later on. So adding a catalyst does not change the energy of the reactant particles. The curve doesn't shift left or right, so the particles keep their same energies. But what we're doing is we're dropping the EA to a lower value. And so that means that there are more particles particles with energy greater than this new lower EA than before, and therefore the catalyst increases the rate of reaction because more particles have energy greater than the activation energy when the catalyst is present. The next thing we're going to look at is yield and the Chatelier's principle. Now, it's very important you understand that yield is the percentage conversion of reactants to products. It's a percentage of the reactants that have been reacted when the reaction reaches equilibrium. And there's Le Chatelier's principle defined again in case you've forgotten. I'm not going to go through that again. You should know Le Chatelier's principle by now. So what are the factors that affect equilibrium? First of all, temperature. Increasing temperatures, according to Le Chatelier's principle, favors the endothermic reaction and vice versa. Pressure and volume. Increasing the pressure by decreasing the volume favors the side of reaction with less moles of gas, and once again vice versa. And concentration, increasing the concentration of one species shifts the equilibrium to consume that species, and vice versa. But it's very important you know that adding catalysts, adding more solid reactant, or raising pressures by pumping in a non-reacting gas do not affect the position of equilibrium. They do not affect yield. Look at temperature and yield, and please bear with me because my pen might not be completely calibrated to this board. First of all, we're going to look at the actual Haber process reaction itself as a case study. We got N2 plus 3H2 is an equilibrium with 2NH3. It's an equilibrium reaction, and it's exothermic with delta H minus 92 kilojoules per mole. Now, by Le Chatelier's principle, if we increase the temperature, it's going to favour the endothermic, or in this case, the reverse reaction. But high temperatures mean a fast rate of reaction. So let's have a look. So we're going to favour the left-hand side, and therefore the hydrogen and nitrogen are going to increase, and the ammonia is going to decrease, and it's going to be quite a fast reaction. Now, I always like doing nitrogen first, and I'll talk about why in a minute. So we know the nitrogen is going to increase, so it's going to say the nitrogen, say, will go up to this value here. It's going to reach equilibrium, and it's just going to come down and match up there. The reason I do nitrogen first is it's the 1 in the ratio. If whatever I change nitrogen by, I change the hydrogen by 3 times as much and the ammonia by 2 times as much. So the hydrogen concentration has to go up by 3 times as much as the nitrogen one. So 1, 2, 3, it'll end up about here, and once again it reaches equilibrium, and then it'll drop back. The ammonia is going to drop down by twice as much as that, so it's pretty much going to drop almost to 0, and there we have it. And it's going to reach a position of a new equilibrium, so we should probably just recognise that a new equilibrium is established, and therefore we see that all these lines will head off in an approximately straight line. Not so easy to draw on this, but that's what it's going to look like. It's quite a fast reaction because it's high temperature, but we're going to favour the left-hand side. Now, down here, by Le Chatelier's principle, decreasing the temperature favours the exothermic, or the forward reaction. But because it's low temperature, it's going to be, not here it says fast, it's going to actually be a slow rate of reaction, because low temperatures give us a slow or low rates of reaction. So once again, we start with nitrogen. So let's change the nitrogen first. Let's say it's going to drop. Let's say it's going to drop by this much down to here. So it's going to level off, and it's going to slowly climb up to there. The hydrogen is going to change by 3 times as much as that. So 1, 2, 3. It's going to end up at approximately the same spot according to my diagram. And the ammonia is going to go up by twice as much. So it's going to end up somewhere around there. It's going to peter off like that. So it's taken a long time to reach equilibrium, but this because it's low temperature, but this time the forward reaction has been favoured. Now, a little hint, if you ever see, or if you're ever given the equilibrium diagram, if all species are changing smoothly, so there's not a single peak, or all 3 of them are peak, they all just change at the same time and change smoothly, it must be a temperature change. Pressure, volume, and yield. Now, there's a relationship between pressure and volume. If you have a container of gas, and you suddenly increase the pressure by decreasing the volume, which means you've squashed this container. We're squashing that container down, so now it takes up a much smaller size. That means those particles of gas are now all in a smaller space. That means if you drop the volume, you increase the pressure. And that's what this is all about. We're decreasing the volume, which means you get an increase in the pressure. So if you do increase the pressure by Le Chatelier's principle, the sign of reaction with less moles of gas is favoured. So in this case, if we increase the pressure, we're going to favour the ammonia side. But one thing to note is if you do increase pressure, you're going to see a sudden increase in concentration of all the species, because by increasing the pressure, you're effectively increasing the concentration of a gas. And if they all jump up, they'll jump in the ratio of what they're already at. This is not the mole ratio they jump up in. They jump up in the ratio of their current concentration. So if we say the hydrogen jumps up to, say, here, it's increased its concentration by half again. That means each of these species will need to increase their concentrations by half again. So half of that height there is about there, and nitrogen is going to increase its concentration by half as well, it'll jump up to about there. So if you see a sudden spike in all the concentrations, that means the pressure has gone up. Also, we talked about in one of the previous slides that if we increase the pressure, we increase rates of reaction. These two diagrams are going to show you different pressures. This is going to be quite a fast reaction because it's at high pressure. And we've said we're favouring the right-hand side, so the nitrogen content is going to drop. Let's say it drops down to here. All we got to do is draw a line up. Hydrogen is going to drop as well. Hydrogen is going to drop by 3 times as much as the nitrogen, so it might drop down all the way down to there. And the ammonia is going to go up by twice as much as the nitrogen, so it might rise up to about here. But note, we saw that spike in all 3 concentrations, which means the pressure has gone up. The next situation, though, is this time we're increasing the volume. We're making the volume of our container bigger, which is going to drop the pressure. Therefore, by the Chaplet's principle, we'll favour the side of reaction with more moles of gas. It's going to favour the left-hand side of nitrogen and hydrogen. But we've dropped the pressure, which means all the concentrations are suddenly going to drop this time. So I'm going to drop them all down by half. So hydrogen first, its concentration is going to drop by half. The nitrogen's concentration, it's going to drop by half as well, and the ammonia concentration is going to drop by half its value as well. So that all the concentrations have suddenly dropped. That's a sign that the volume's increased or the pressure has decreased. And we're favouring the left-hand side this time, so the nitrogen's going to go up from where it is. Let's say it goes up to here. All we've got to do is draw now our curve. Hydrogen's going to go up by 3 times as much as that because it's of the ratio, so it's going to come to about here. And the ammonia is going to drop by twice as much as that, so the ammonia is going to drop down to a very low, almost 0 value in this instance. So there we go, and that's the big clue. If all species have a sudden concentration change, an increase or decrease, that means we've got a volume/pressure change taking place. What's next is concentration and yield. Now, via the Chaplet's principle, if we add a species, it'll cause the equilibrium to shift to consume that species. So in this case, if we're adding nitrogen, it'll cause the reaction to shift to the right to consume that nitrogen and make more ammonia. But how do you know? How do you indicate in the diagram, or how would you know that nitrogen's been added? Well, if you see a sudden spike in one species only, that means that species has been added. So if we're adding nitrogen, let's just say the nitrogen is going to jump up to a high value. For some reason, we've pumped in extra nitrogen. That's what it's going to look like, a sudden spike in nitrogen content. But we're shifting it to the right, so the nitrogen content is going to drop. Let's say it drops down to here. The hydrogen is going to drop by 3 times as much. That'll be down to here approximately. And the ammonia is going to go up by twice as much as that value. It might rise up to something like there. And we can tell we've added nitrogen. 2 things, the reaction shifts to the right, but also there's that initial spike in the nitrogen content. On the same sort of token, via the Chaplet's principle, if we remove a species, it's going to cause the equilibrium to shift to try and replace that species. And in this case, just like they do in the Haber process, they pump out ammonia. So we're going to represent that by showing the ammonia concentration alone dropping. So only the ammonia concentration dropped all of a sudden, which means we're only pumping out the ammonia. And because it's shifting to the right, that means the nitrogen and hydrogen is going to get consumed. That's not what I wanted to press. Let's see the green button this time. So the nitrogen might drop down to here. The hydrogen might drop down to, let's say, 3 times as much, about there. And then the ammonia is going to jump up by twice as much from this spot. So it's going to jump up to about here. Okay, and that's the clue. If you ever see one species alone suddenly spike up or spike down, that means that species has either been pumped in or pumped out. The last thing we're going to look at in this set of slides is catalyst and yield. Now, adding a catalyst increases rate of reaction, but doesn't change the yield. Therefore, it does not change the position of equilibrium. So the concentration of species at equilibrium will not change. So adding a catalyst at time 0, if we start this reaction again adding a catalyst, what's going to happen is the reaction is going to happen much faster. We'll reach equilibrium much quicker. Very, very, very quick. It'll come to the same position of equilibrium at a very, very, very short time. So all these curves will be much steeper to reach equilibrium. But note, they all come to the same position. It does not change the position of equilibrium. The catalysts do not affect the yield. Now, if we added a catalyst at time t, an interesting question in one of the trials this year, the answer is nothing will happen. Okay, the catalyst will just sit there because it's already reached equilibrium. The catalyst won't make it reach equilibrium any faster. So what it will do, the catalyst will just sit there, and the reactants will stay, and the products will stay at their same concentrations. However, if after we added the catalyst, if we then change conditions, say we change temperature or pressure or concentration, after we added the catalyst, we know that at changing temperature, pressure, or concentration changes position or equilibrium, and because the catalyst is there, the reaction will happen much faster now the catalyst is there. But if we just add a catalyst at equilibrium, we'll see no change whatsoever.